So it's my pleasure to introduce this session, actually plenary too, sorry, from data to decisions, leveraging AI to prevent SUDEP. It's probably impossible to go to any meeting, any seminar, any podcast without AI appropriately being discussed. And so we are in for a treat today with our speaker panel. What I'd like to do is sort of give you the overview of what you're going to hear, and then we'll go speaker by speaker. So Teresa Prego is our first speaker. Teresa is the lived experience speaker. She's going to talk about what technology has meant to someone whose daughter has epilepsy. And it's sort of special because Teresa is a leader in epilepsy-related monitoring technologies. So we're going to get knowledge from someone who walks in both worlds. Dr. Sam Lhatoo is going to talk about artificial intelligence in epilepsy as an overview. I think if you just do a search on AI in epilepsy, Dr. Lhatoo's name will come up. I've asked him to be as superficial as he possibly can with his large fund of knowledge, just to be able to introduce the various aspects of how AI is relevant today in the world of epilepsy. Dr. Oman Magana-Tellez is going to talk about sleep staging as biomarkers for sudden unexpected death in epilepsy. Why is this relevant? Because as we know, the majority of SUDEPs occur during sleep. Thus, there's the potential for clues, biomarkers that occur during sleep. His work is focused to determine if there are biomarkers that could determine susceptibility to SUDEP. And again, just think back, everyone gets a routine EEG who has epilepsy. If sleep were captured, wouldn't it be fantastic if there was a marker to identify individuals who are at increased risk? Dr. Cui, who will be speaking to us via video, is going to talk about natural language processing approaches to SUDEP. For those of you that remember the film, the TV series, The X-Files, the subtitle, The Truth is Out There, that's how I sort of look at medical records. There's a phenomenal amount of information that's in medical records, but we don't always have access to it just because of its volume and lack of standardization. Dr. Cui's on the cutting edge of the technology that makes such knowledge accessible to us. Our last speaker, Dr. Ben Brinkmann, will be talking about seizure forecasting, sort of the holy grail. As you know, one of the great impacts of having seizures is never knowing when they're going to happen, that raw and uncertainty. Wouldn't it be terrific if that could be resolved in some way? And furthermore, if a medication could be delivered just when it was needed before the seizure happened. So those are the topics that we're going to discuss today. And with that, Ms. Prego.
Thank you, first of all, for the opportunity to speak to you and to introduce you to my family. These are my kids. This was at my niece's wedding, and it's also our seizure dog, Honey, who's become part of our family as well. So everyone that lives with epilepsy, and Tom Nugent did it earlier, knows the day, right? And maybe there's sometimes several of those days when the world changes. So for us, it was on January 1st, 2001, when our 5-year-old, or then 5-year-old, came into the bedroom early, laid on the end of our bed, as some of our kids would sometimes do, and immediately began to seize. She was a normally developing 5-year-old, had never had a seizure, she did not have a fever. As a former EMT, I knew what was happening, but I did not understand at all what was happening. So when you live and you enter this world of epilepsy, there's fear, there's hope, there's anxiety. I don't know if any of you saw the story in the London Times about the woman who said, basically each day I get up and I'm afraid of, what I might hear about my son with epilepsy. So what do we do as parents? We want to fix it, but how do you fix it? So this is a photo. We were a running family. We were at a family running event, a warm day in the summer. It was sort of humid. I knew that heat and humidity were triggers for my daughter's seizures. They often went into status, so we were hypervigilant. But I thought, we're in a grassy area. Look at all the grass in that photo. It'll be safe even if she falls, so I'm going to take like 2 minutes and go to the porta potty. In that 2 minutes, she had a seizure, she fell. She found the one square of concrete in all of that grass, scraped her face across it. You can't see it in this picture, but on the side of the face, there's a big scrape from the seizure. It's the only time I've had a police escort out of a porta potty line. So my 4-year-old came running over with a police officer behind and said, "Mom, can you come over?" So, you just don't know. And so for me, with a training undergrad as an engineer, data is key. So I gathered all the data I could. What are the triggers? We know it's heat, humidity, sometimes time of day, sleep. Weirdly, if she had a certain kind of ice cream, black raspberry ice cream, we'd almost always get a seizure. Probably it turns out it's the dye that's since been banned. But, there are things that as a parent, as a family member, that are happening. So I would take all of that information. We were treated at Boston Children's at the time, and I would bring it into every visit, maybe excessively. So the clinician would always refer to me as mother, and it was stated in a way, mother with a capital M. And several years later, when she became an adult and we needed to transfer her records over, I went to Children's to get the records because some of them were physical paper records. So out of curiosity, was just reading through, and you can see some of the notes. It says mother, and it was indeed with a capital M, so I wasn't imagining that. Very engaged, provides much information, read into that excessive information. I do recall an encounter with the clinician, who is wonderful, and I said, look, I have all this data. I built an algorithm for her to predict when she would be at higher risk. And he just looked at me and said, what in the world do you want me to do with this? And my response was, fix it. And if you can't fix it, can you at least make it better? So maybe I was on the way on the end of the spectrum of the data, but there's a lot of good data that family members, that individuals, that people in the ecosystem that aren't the epileptologist or neurologist have. So my proposal for the AI development team here is let's look at large language models, but also how do we look at I'm going to call it an LM, and I've not yet published on this, so it's not really legit. But how do you get that family data in there too? So there's data out in the world that we'll utilize, but then how do we personalize it? Because, in our household, every one of us can tell you if today is a day that a seizure is more likely than another. Some of it's intuitive, some of it's just temperature and humidity still. And then how do we incorporate that? And if we can't fix it, how can we at least make it better? So where are we now? We have gone through a resection. It was partially successful since most of her seizures evolved into status early on. The resection did help that. She has an RNS implanted. That helped to some extent as well, but still dealing with seizures at least 6 or 7 a month. So that, that impacts your life. So she recently graduated with a degree in fine arts. It took 9 years, 3 schools, 1 dog, and then there was a brief interlude where there was a RNS battery replacement that didn't go as smoothly as planned, so there was a semester off involved as well. But, the fact that a village can come together and utilize technology, utilize therapies, partnering with our clinicians to get to a point where a kid who's really creative can actually get a degree in fine arts and succeed. But If I look back, as a kid, Gabby went to Camp Weekend 2, which is a wonderful camp that the doctors at Brigham and Women's and the nursing staff, probably more importantly the nursing staff because they ran the show, had for kids with epilepsy. So you could go to camp, and if you had a seizure, it was no big deal, which anyone in this room who is a parent of a kid with epilepsy who's ever tried to send them to a non-epilepsy related camp can relate to. It's stressful, often they're rejected, and it is a big deal every time they have a seizure. So there was a gang of 5, we called them, these kids that had been at camp since about age 5, starting with the day camp and then going to an overnight camp. And, they loved that camp. But if I look at it now, the first one we lost was in 2013. And when Rose passed away, we were all at the funeral. None of us, until that funeral, had heard of SUDEP. But Rose passed away from SUDEP. So here's a group of campers, all high risk, all refractory, all the parents talking amongst ourselves, and we didn't know. And then John, also part of that gang, passed away this year, and his parents knew that he had a seizure every morning, heard the seizure happen every morning, and then usually he would, turn over and recover a little and then come downstairs. One morning, they heard the seizure, and then when he didn't come down in the usual time, they went up. They had not heard that second seizure, and by the time they found him, he could not be resuscitated. So there's no such thing as sort of knowing what's safe or being able to predict. So, of that gang of 5, 2 passed away from SUDEP, and Maddie passed away post a surgery that did not go as well as anticipated. So that's hard for a kid who's not yet 30. These are, 3 of that gang who just didn't even make it to 30. So our ask as our family, and I think our ask as parents overall, is, the same thing I said to the doctor many years ago, can you fix it? Can you use technology to fix it? And if you can't fix it, can you at least help it? So these are great shots of all over the place. Disney is a prevalent theme, concerts. The thing that's happened in each of these shots is a location of a seizure as well. So, if we can use technology to help people just be able to live their lives, to optimize, to help them feel that they are empowered, that they are informed, that they're part of the equation, that's the ask. And can we, as a group, collectively utilize technology to enable improved care, improved solutions, improved quality of life for people living with epilepsy? And I'm going to quote, if I can get to that page, just a thank you to everyone in this room and everyone in this community who has worked hard over the years to provide better solutions. That picture in the corner is a Meg. I don't know if anyone's had a Meg. Probably many of you have or have experienced them. But that looks like an alien sort of warship. But that was the early version of what's now a standard of care for understanding what's happening deep in the brain. So as Mother Teresa said, do good. Even if you're not rewarded for it. I don't think anyone in this room is in this room because you think you're going to make a lot of money doing what you do. But do good. And a lot of good has been done and will continue to be done. And I'm going to end with a quote from one of my favorite characters, Purple M&M. I did try to get her here for us, but apparently Purple does not do in-person visits. But Live, Love, Laugh, Purple is her theme. And I'll leave you with that. Thanks.
Thanks, Teresa. That was terrific, inspiring, and really, set out a mission for us. One of those people that has done a lot of good is our next speaker, Dr. Sam Lhatoo. Dr. Lhatoo is professor of neurology at the University of Texas and has really been a prime mover in uncovering mechanisms of SUDEP for over the last decade. So with that, Sam?
Thank you. Thank you, Jeff, for that kind introduction. I have a couple of disclosures. Are we moving? No. Yeah, I've done that a few times. Yeah, so while that's being done, a couple of disclosures. In the main, I'm not an AI expert, so there's a healthy dose of imposter syndrome going on here. I don't have a computer science background, but like many people, we have been using machine learning, deep learning, and AI tools in the research that we do more and more. So I've organized my talk in a way that I would want AI explained to me. So to that one MIT professor in the audience, apologies. The other disclosure, of course, is that I did indeed use ChatGPT for some sections of my talk. Yeah. So AI, these are basically, there are many technical definitions, of course, but we're referring to computer systems that perform tasks that we would expect human intelligence to. Okay? And the traditional view of AI has been a rule-based kind of system. If this, then that. So if there's loss of consciousness and shaking, for example, then we're dealing with seizures. Of course, things have moved on, so now we have learning systems. So machine learning is where the computer learns patterns from data, but it's actually humans who feed the inputs, the features that the model then learns. So, for example, a model that predicts SUDEP, for example, would be the features could be convulsive seizure frequency, the presence of breathing problems, the presence of slow heart rate or bradycardia, and things like that. So a level above that is deep learning, and this is a system where the computer learns patterns from the data, but it picks its own features. And so this is where the concept of black box models comes in. And an example of this would be where the computer model learns how to pick an epilepsy focus from MRI scans, for example, but doesn't necessarily get told what features to pick. And then there are generative systems. So these are models that can create new content. And in the medical context, and I'll speak about this a little bit more, there's something called ambient abridge, which many of the clinicians in the room might use, for example, where you have an AI-based listening device that listens to a doctor-patient conversation and produces a structured note for documentation and does that kind of stuff. And then you have learning by feedback systems, where the model becomes better and better at performance through trial and error, and an example could be a model that chooses the best drug for a given patient for their particular situation. So how does medical AI actually work? So most of it is based, as I said, on machine learning and deep learning systems. So these are systems that link statistical patterns from various inputs. It could be MRI scans, could be EEG, could be electronic health record, notes, and then there are outputs. So this could be a diagnosis, could be a risk index, recommendations, and so forth. So the models are trained, or we call it training set, and then of course the model has to be tested on a testing set, and that testing set should necessarily be a set that is not where the model was developed. So that's what we refer to as external validation, and this is very important in the development of AI models. So it's important to understand that, of course, AI does not perform like a human doctor. It only recognizes patterns and correlations. And so there is no such thing as a doctor AI. Most of the tools that we use right now are what we call narrow AI. But there are people who believe that eventually the doctor AI concept will become a real thing. And then what's topical also is agentic AI. This is already being trialed in the electronic health record in some systems across the country, inside Epic, for example, where the model can pick out an abnormal test, let's say abnormal liver functions, put in an order for liver ultrasound, and then wait for the doctor to sign off on it if they think it's truly appropriate. So what are the different types of AI models? So there are large language models, and you're all familiar with ChatGPT. There are generative image models. So this is proof that imaging AI is not quite there, Jeff, because I think the original cuts a far more dashing silhouette. Then you have audio and speech models, and of course you've seen TikTok and Instagram videos where prominent people are impersonated, for example. There are time series models where we're looking at EEG for brain-computer interfaces, for example, and that's what Elon Musk is doing with Neuralink. Video models, like I said, TikTok, Instagram, there are daily examples of things like that, and there are many others. So there is something called the Gartner hype cycle for new technologies, which says that when there's a technology trigger in terms of visibility, there's a peak of inflated expectations, very high expectations, and then, of course, there's a trough of disillusionment, and then there's a slope of enlightenment, and then a plateau of productivity. So this is the Gartner hype cycle. And so in some things, with imaging, for example, and so not so much with epilepsy imaging, but imaging in general, stroke, for example, coronary artery disease, it's very much there. It's used every day and highly effectively. With EEG, we're kind of on the downslope a little bit. We're figuring out what things currently are possible and what things are not. And in terms of agentic AI, there is very much this expectation that it'll be amazing, and we're not so sure that that's going to happen anytime soon. So compared to these early headlines, we're a lot further ahead in terms of the presence of AI in our lives. So here it's worthwhile talking about a bridge. So this is a tool that I use every day. There are probably many clinicians in the room who also use this. So this is an app that sits on my phone. So when I go in to see a patient, I talk to the patient. I don't have to look at my keyboard and the computer screen anymore. I can have a fully engaged conversation with the patient. This device is listening. It can actually translate 14 different languages. And by the time I get back to my desk to write my note, it's already there. It's structured. It's pretty amazing, put together pretty amazingly. And all I have to do is check for accuracy, edit it, and boom, we're done. And of course, this recent paper from the New England Journal group of publications shows that it's fantastic for physician burnout. And I believe that it's great for patient care too, because I can actually focus on the patient in front of me. So this is narrow AI, but more and more these things are coming in to practice. So how do we classify these applications? There are various ways of doing it. So you can classify it on the basis of whatever signal you're studying. So it could be EEG, imaging, video, et cetera, of course, the electronic medical record. So these are acquisitions. You can classify them on the basis of clinical workflow. So it could be diagnostic, and there are examples, etiology, electrophysiology, videography, gene diagnosis. Then there's the monitoring classification. So these are, and we'll hear about some of this later on, rapid EEG, wearable seizure alarms, forecasting and risk stratification. That's another way of classifying it. Therapeutic, of course. There's RNS, DBS, and long-term disease management that's based on EHR, and what we get is outcome prediction from these. Somewhere down the line will also be SUDEP risk AI. Then there's the back-end algorithm classification, so what's under the hood, and so this is of interest to academics, what tools are actually being used and developed. So here we talk about core models, so there are things like CNN, RNN, transformers of various kinds. So you can look at EEG models for analysis that are time series based. You can also look at EEG as images. And so there are models for doing that kind of stuff. They're called vision transformers. There's video and audio, of course. There's neuroimaging, of course, EMR again. And more, we see papers where people are fusing these models together to achieve their goals. So you can classify things like that. What's very important is FDA class. So how do you determine FDA class? And that's really to do with risk to the patient and the level of clinical oversight needed. And then, how easy it is to get FDA approval is to do with whether there are exemplars, predicates that are already out there, and sometimes, of course, they're not. And then you have to pursue de novo approvals, which can take a long time. Since April this year, the FDA also mandates that because, in real-world usage, the algorithms can change, have to change, et cetera, that there be a predetermined change control plan. So these things are all FDA considerations. And what eventually is spat out is class. So low risk is, the stuff that you use for doing EEGs, electrode gels and electrode caps and so forth. Class 2 is moderate risk, and the vast majority of AI tools lie in this particular group. So here, it can be to do with seizure prediction, seizure detection, and various things like that. Class 3, so the wearables are all lie inside class 2. Class 3 is where the tools actually deliver treatment, for example. So, RNS is an example of a tool that delivers treatment, although they don't actually use AI in a patient-facing way currently, but those are class 3 devices. So there are many of these that are going through FDA approvals. Some of them are already here. So the empaticas and the braces and so forth are already approved. So those in the red are those that have been approved. There are others that are being developed, and these are all examples of them. MRI lesion detection, surgical trajectory planning, et cetera, et cetera. So many of these. There are also electronic health record-based cohort builders that are used for clinical trials. These are commercially available tools that you can actually subscribe to. So in the epilepsy space, what are the things that are currently being used? Most of these are tools that are referred to as software as a medical device. So you have EEG-based software as a medical device for seizure detection. So the clinicians in the room will recognize some of these names: Cerebell or Rapid EEG, Persist. Natus now has an AI tool. There's NeuroMatch. NK has its own, and so on and so forth. There are also EEG software as a medical device that does not do seizure detection. Post hoc, it looks at EEG, and we'll talk a little bit about this as well, where it detects abnormalities and classifies them. So an example of something that's in clinical usage is rapid EEG. So you see the little cartoon figure there where there's an EEG belt that's applied around the head. It's very easy to do. It's done in minutes as compared to conventional EEG, which can take a pretty long time to set up. And it connects to that little handheld device by the bedside. And there's an AI tool which is FDA approved and tells the people at the bedside whether a patient is in status epilepticus or not. And this is something that we use in our hospital system very effectively. So here's a picture and a video. What you see in the bottom panel is a probability tool. And so you see that little peak there. It's a little peak there, which tells us that this particular patient is in status epilepticus. Whoops. Oh, can you play that? Anyway, so again, the clinicians in the room will recognize that this patient has a seizure record, if the patient is in status, and there's a tool telling us that at this particular time, there's a 90% probability, 90% greater probability that this patient's having seizures and is in fact in status epilepticus. So a very useful tool that reduces the latency to actual intervention. So what's under the hood? What do? They organize EEGs in these 10-second epochs that are then, with an AI tool, computed into 5-minute segments that tell you what the seizure probability is. And a bedside alert is issued, so the treating team knows very quickly what's going on and whether they can jump in. So this is an example of an AI tool that's used at the bedside and used quite effectively. So the evidence for it is pretty good. I think the company have been careful in organizing the evidence to show utility. You can see these graphs here that give you the statistics for how useful the tools are. So there's very high negative predictive value and somewhat of a low positive predictive value. But what this translates to in clinical practice is that it's great for ruling out seizures. It's not great for catching all seizures, but really in the emergency setting, you don't want to miss these seizures. So there's a potential for overtreatment perhaps, but in a patient who's in trouble, that overtreatment really, the benefits are far greater than the risks of not doing anything. So this is an example of a tool that's used in practice currently. This is AutoScore built by Holberg EEG, which now is available in the Natus EEG acquisition. So this is a study in JAMA Neurology which looks at its utility. So what this particular tool does is that it is able to look at an EEG, it is able to tell you normal from abnormal, and if it's abnormal, it's able to tell you whether the abnormality is epileptiform or not epileptiform. And that little table in the top right corner shows you that this tool behaves or is as good as human expert readers. So this is not a tool that I've used personally, but there may be some folks in the audience who do use it. But this is an example of EEG reading. It doesn't detect seizures in real time. That's an important distinguisher from rapid EEG, but it considerably enhances the effectiveness of people's times when they read EEG. So this is an example of how the electronic health record can be used for epilepsy. So this is a paper from Patrick Quant's group in Australia, and what they looked at was many, many patients who were newly diagnosed with epilepsy, followed them up for up to a year to see whether they became seizure-free or not, and then used a machine learning tool. It says deep learning there, but really it's a machine learning study. They fed in 16 different inputs into the model. You can see them all listed over there. And what they found is that the number of pretreatment seizures, so if there are a lot of seizures, for example, before diagnosis, if the patient had psychiatric conditions, if there were abnormalities on the EEG or MRI, then these predicted a poor outcome. And so this is now, in fact, a multi-center study that's being done across several institutions. And if successful, these are tools that can be embedded in the electronic health record. The moment you see a patient, in the individual patient, you may be able to use this AI tool to determine prognosis. There are, of course, a lot of video tools that are out there. There are several startups and companies that look at AI-based video analysis of EMU seizures, for example. What's very interesting about this particular study, and the reason why I've highlighted this, is that this is patient-facing. This is from Meisel's group in Germany. And what they did was they looked at children with infantile spasms and normal children. They created this AI-based tool using a vision model, which was very effective. And then they validated it with TikTok videos and YouTube videos of seizures, and further validated it in the EMU with patients who were seizing. And they found that this actually performed very, very well. So this is actually something that can be used in smartphones, is patient-facing, and could be a very useful tool for parents and carers, and of course physicians who follow up with them in the clinic. So these are things that are all coming. Of course, imaging, like I said, this is a paper from the MELD project, Epilepsy Lesion Detection Project. And they used, again, AI tools to do this kind of thing. So in the images you'll see in green, the ground truth. So we know that there's a lesion there that causes epilepsy. And in red is where the machine predicts that the problem is. And you can see there's a lot of orange because there's so much overlap. The machine performs remarkably well in identifying these lesions. So these are not available in clinical practice yet for epilepsy, but they will be coming soon. So I'll conclude by saying that there is no Dr. AI yet, as you've seen. There's just narrow AI, but it's here. And a Bridge Ambient, this EHR tool that I use, for example, it's in a lot of institutions being used very successfully. In epilepsy, we're a little behind, but we're catching up. rapid EEG is an example of clinical utility, and as I just mentioned, in imaging and so forth, these tools are going to come. So video AI, what you saw was just infantile spasms, and as you know, seizures are very heterogeneous. It's going to be a challenge to tackle all types of seizures, but that too, I believe, will come. And so we'd better get used to it. And I think this is a famous newspaper story, at least in the UK, about how we can get it wrong if we are too Luddite. Thank you.
Thanks, Sam. I guess the future is now. Really, really quite spectacular. Our next speaker is Dr. Magana-Tellez, who's going to talk about his work in sleep. And he is currently a research associate at the University of Texas, where his work is focused on biomedical signal processing. Please.
Thank you very much, everybody. Like Dr. Bhatter said, I will be talking about the use of AI in sleep staging for the biomarkers of sudden unexpected death in epilepsy. So pretty much a quick outline of the presentation. First and foremost, we're going to talk a little bit about why it's important to study sleep. I mean, it's been mentioned quite a while at this conference, so we're just going to add a little bit of extra facts for it. We're also going to discuss what is the current problem of doing sleep staging in the EMU, and how the AI tools that we use are able to give us and overcome this obstacle. Moreover, I will share a little bit of the potential sleep biomarkers that we found in our SUDEP cohorts. And of course, we're going to end up with what's next for the future to work on. So why study sleep? We spend at least 1/3 of our lifetime sleeping, which is anywhere between 25 to 27 years, so it must be some sort of important. It's not really a new idea. It's been started all the way back to 450 BC with the ancient Greeks, when they were also wondering the exact same thing about what was the whole thing. We know that it is fundamental for the development, learning, memory consolidation. It has been related to multiple different health systems, such as cardiovascular, respiratory, and it's divided into 5 different stages. They are considered awake, non-rapid eye movement or non-REM stages 1 to 3, and REM sleep. Usually the non-REM goes from a slowing and synchronization of the brain. And for the case of sleep homeostasis, sorry, there are no images there. There should be a little bit of images, so that's going on for. But with regards to sleep homeostasis, is a process in which the body is able to rest and recover. And the way that we quantitatively measurement is that we take the slow wave activity of the brain, so the specific waves that generate in a really slow frequency around 0 to 4 hertz or 4 beats or 4 events per second. And if we can track them throughout the night during non-REM sleep, they reflect the need for sleep or the why we need to sleep, and it actually shows a line that decreases. So it starts high at the beginning of the night because that's when we need the more rest, and as our body recovers and rests, it slowly becomes low towards the end of the night when you're pretty much recovered, so it should be a low value for it. We also know that in regards, oh, there you go. So finally catch up. So this is exactly what the sleep homeostasis looks like. So it starts high at the beginning of the night, and as the time progresses, that line slowly decreases, meaning our bodies are recovering and we are resting. In the case with sleep in epilepsy, as has already been mentioned before, well, we know that seizures tend to happen more during non-REM sleep, and in the previous panel, they would show us a really good idea and discussion why, but it mostly has to do with the synchronization of the neurons in the brain. But they also form this vicious cycle in which people who have seizures during the day, they tend to have a very poor sleep during the night. That means that they don't have a poor sleep in the night, which means the seizures get worse the next day, and we move and so on and so forward in this vicious cycle that affects a lot of people. There we go. We also know that SUDEP is highly related during the sleep, as most cases have been reported near or around a bed. And we also know that nocturnal generalized tonic-clonic seizures are also considered a major risk. So people and patients who have that must be taken care of because they are more at risk of SUDEP. So through all of this, we know that sleep is very important to look into epilepsy, but then why is it not most commonly looked into during the people's stays at the epilepsy monitoring unit or the EMU? Well, first and foremost, although the equipment is very similar to the ones that exist in the sleep labs, it's not really designed, or more places do not have it properly acquired for what we need. Specifically, the channels are not arranged the proper way. Some measures, such as muscle reading or eye reading, are also not implemented. Or sometimes, the patients are just not willing to go through it, so obviously we cannot force them to do so. Moreover, there is a lack of what we call like sleep baseline. Patients are usually not asked, how is your sleep? Do you have any difficulty that you do? Anything you wish to report? This type of behavior that we observe, is this like normal for you or not? This type of information is really not available for us to study when the patients are there. There's also, during the stay in the EMU, we don't talk about patients about, do they have this many naps? Do you have any trouble sleeping last night? How would you categorize this versus your previous sleep? So we're really missing that piece of information from our patients. Moreover, if we don't have someone who is an expert in sleep staging, then we need to bring someone in to be able to do this process. And that means that sometimes we have to deal with interdepartmental problems. We have to bring someone from the sleep lab. They might be available, they might be busy, etc. And of course, the last but not least, during a stay in the EMU, your sleep is not the normal sleep that you normally get. You're hooked up to a lot of machines, you're in a strange place, there's people walking in and out at all times during the night, so it also does not reflect what you normally would sleep in your own place at home. But to this process, one second, there we go. So how do we analyze sleep? So the way that is done by order of the Academy of Sleep Medicine, we take 30 seconds of EEG signal. And in those 30 seconds, we analyze for certain features, such as the frequency or how fast the signal is, the amplitude or how big the signal is, or very specific features on landmarks in the signal, such as eye blinks or movement, that would tell us whether or not the patient is in one of the 5 stages that I spoke previously. So if we take those 30 seconds and we reflect them into this little bar, the green bar represents a full 8 hours of sleep that normally we should all get. If we scale it properly, that is exactly how long 30 seconds is, considering the whole 8 hours. So that means that visually a human has to go through one of those stages, one by one, analyzing, telling us what is the sleep stages, and then moving on to the next 30 seconds. We continue with this process. Let's say we're moving throughout the night, but what happens when at some point we discover that one of the stages that we thought it was the landmarks that we're using or the features that we're using are actually not related to the sleep stage, or they're mostly related to epilepsy or any other factor. That means that we have to go back pretty much the beginning of where we analyze that sleep stages and then redesign and rediscover this process, which it's a very tedious process. And again, the focus is to work on the epilepsy, so it's not really well done during the stay of the EMU. So this is the area or the niche that the AI is also helping us into, how we can speed up this process and make it much easier for both researchers and epileptologists to look into sleep. This model, which is a deep learning model, like Dr. Lhatoo explained previously, it is what it's called a black box model, meaning it's really not known what's happening on the inside, but once we give them an input, it gives us an output because the network figures it out by itself. In general, this model that we use, it was published as open source. It was developed by Jaud et al. And colleagues. And the way that it works is that it was trained on 6,431 patients' sleep nights. Some patients have one, some patients have multiple nights. And they were from all variety of sleep areas, including normal sleep study, obstructive sleep apnea studies, dementia, as well as epilepsy. Briefly to explain to you how it works, we begin by the input. So the input is the exact same as what we do in the normal sleep staging. So we give it 30 seconds of signal with a specific sleep montage, which are 4 channels, usually located in the center of the head, because that's where we can look at the best features for sleep. While the data is going through the inside of the network, it's divided into 2 big chunks. The first one, which is a convolutional neural network, the idea is that this network will take all that data that we inputted and then crunch it down to give us the specific features that are useful to detect the sleep stages. Moreover, the second part of the network is what we call a recurrent neural network. It actually takes temporal information or time into account, meaning it also looks around before and after during the night, and those 2 combined together will give us the correct or the closest approximation from the sleep output, which is going to be what sleep stage the patient was in those 30 seconds of signal that we gave them. We, of course, tested this with a sleep expert to make sure that it was working properly and we were not committing any type of mistake. We selected, by the way, we use the Center for SUDEP Research, or the CSR database, which has a large number of patients on it. We selected 8 patients randomly, and we just did a sleep staging manually with our sleep expert. When we took it with the sleep expert, it took us about approximately 12 hours, considering both the time that it took us to analyze it, as well as sometimes he was not available, so we had to wait for him to be available. So it was a long process. When we do it with the automatic network, it took us around about 40 minutes, going from the process of actually taking the data, putting it into the network, and giving us the output. So it's a much faster system. What I'm showing here right now on the left is what we call a confusion matrix, but the idea is that we're comparing what the human was classifying versus what the network was doing. So in the upper left corner, we see that when the expert said, or the human said that it was awake, 94% of the time the network agreed with it. When the human said it was non-REM stages, it was around 84% of the time that the network agreed. And finally, when we said it was REM stage, then the robot agreed as well. All in all, it was approximately around 90% of performance accuracy, meaning that 90% of the time the network and the human agreement matched, which gives us a little bit of trust to continue moving with this investigation. So the work that we did, like I mentioned before, we took the data from the Center of SUDEP, or the CSR database, in which there are 41 patients who later died of SUDEP. The difficulties that we're talking about having nights means that only half of those patients had a full night recording that we could use for this experiment. Then out of those 21 patients, spread around evenly between male and female, we compare them with age and sex match between the other 3 categories that we designed. The first one is the high risk of SUDEP, which are people with epilepsy which have at least one generalized tonic-clonic in their medical history. If you recall at the beginning of the talk, that's one of the highest risk factors that it is for SUDEP. We also compared to those called low risk of SUDEP, which are, again, people with epilepsy who do have the epilepsy, but they do not have any generalized tonic-clonic in their medical history. And finally, we also compared them to the control group, which are patients who do not have epilepsy, but they still took an entire night on the EMU. So all in all across, we had around 84 patients that we were analyzing their full nights. So if we want to do this manually, it would have taken a really long time, and we probably want to wake it up halfway through. But thanks to the algorithm, we were able to do it in a relatively fast fashion. So this is the large outcome that our work done. On the figure on the left, we can see that we compare all 4 groups, and we're looking to see how their night rest or their sleep homeostasis graph look like. In the case of the high risk, low risk of SUDEP, and control patients, we do have that recovery or rest, meaning they begin high at the beginning of the night, and as the night is progressing and they're resting, the slope becomes more and it becomes slower at the end of the night. But what we discover is that the patients or the people who later died of SUDEP actually are showing the opposite. Their need for rest actually increases throughout the night, which is telling us that they're not really recovering and they're not resting, which could be a potential indicator of warning that we can then have more aggressive look into the patients to see what the problem is going on. Unfortunately for us, GTCs on its own, which was a very important factor, is not strong enough to be like the golden key, because the high-risk patients also have that normal decline. And because that was the difference between the groups, that means that it's not the only key factor that we're looking into it. So there must be something else in those patients that is not letting them rest throughout the night. Moreover, when we look further into within the SUDEP group, and we plotted out between the date of the experiment and the date of the SUDEP occurrence, we also saw that there is a significant difference between those patients who were closer in that range, from 0 to 2 years, to the patients that were farther away, which is 4 to 6 years, which indicates that there is some sort of temporal change that is happening the closer the SUDEP occurrence goes through. So this could also potentially lead us more into seeing these changes into the patients. We can then turn into more aggressive care for them to hopefully prevent the case of SUDEP. So what is next then? Well, we know that, again, we're saying it one more time because why not? Sleep analysis in epilepsy is very important, so it needs to be looked into it. We also know that thanks to the tools such as this AI algorithm, it is now possible to do faster sleep stagings that we can do in the EMU, which will let us then analyze more and more patients to be able to find out those specific biomarkers that we can find for SUDEP prevention. We have shown a little bit of ones with the sleep biomarkers, but of course there must be something more in the same. Like this is just the beginning of the clue or the idea. And of course, further more elaborate studies regarding how sleep look more into genetics, perhaps looking into medication has to affect, because a lot of medications tend to affect sleep as well, so we need to start looking into that as well. All of these will give us eventually more keys and answers to once we found that important, then perhaps we can implement more and care more for our patients. Thank you very much. That would have been my talk for today. First and foremost, I would like to thank my mentors, Dr. Lacroix and Dr. Lhatoo as well as our people at the University of Texas that helped us with this work, including Norma and Dr. Rossi, as well as in the University of Wisconsin, our collaborators, Dr. Magana-Tellez, who was a sleep expert who helped me with the sleep staging, as well as Dr. Menoliboli for her helpful insight with the sleep homeostasis process.
Thanks, Oman. That was fantastic. And now we're going to hear a talk from Dr. Licong. She's Associate Professor of Bioinformatics at the University of Texas. Unfortunately, she can't be with us today, but I hear we have a video. So perhaps we can play that.
Today, I will talk about natural language processing and NLP approaches to SUDEP. This is a brief outline of my talk. First, I will introduce what is NLP and review several major NLP approaches in general. Then I will talk about several applications of NLP in the epilepsy domain and our recent work on serial frequency extraction to facilitate SUDEP risk assessment. For those who are not familiar with NLP, it is one of the most exciting and rapidly growing areas of artificial intelligence, which transforms how computer or machine can understand and interact with human language. Its application spans from sentimental analysis for detect opinions to chatbots that carries human-like conversations and name entity recognition for recognizing entities such as diseases and like summarizing text. There are four major categories of NLP methods used in clinical and biomedical text processing. The first one is rule-based approaches, which rely on handcrafted patterns or rules and regular expressions, and predefined dictionaries or vocabularies. These rule-based systems are always deterministic, transparent, and work well when the terminology is relatively stable. But they can be very labor-intensive to maintain and may not generalize well to other data sets. The second approach is traditional machine learning-based models, such as logistic regression and support vector machine, which use manually engineered features derived from text. Such methods can improve scalability and performance, but still depend heavily on domain expertise for feature engineering. The third approach is the deep learning-based models, such as recurrent neural network RNN and long short-term memory LSTM, which automatically learn representations from the large text corpora. Such models can capture contextual information better than the previous methods, and also reduce the need for manual feature engineering effort. The fourth approach is the pre-trained language models, like transformer-based BERT models, and the more recent large language models. And these pre-trained language models leverage large-scale pre-training to capture rich semantic information, and can be further fine-tuned for different NLP tasks with relatively small labeled datasets. However, the deep learning-based approach and the pre-trained language model-based approach are less transparent than the first two approaches. NLP has been applied in epilepsy domain for different purposes. For example, the first one, phenotyping and cohort identification, which is to identify who has epilepsy and determine what specific epilepsy subtypes from the clinical notes. And the second example is extracting seizure frequency and outcome information, such as seizure freedom status and last seizure date. And it has been also used for identifying epilepsy surgical candidates and improving neurology clinical care. Another example is more related to my research is extracting SUDEP risk markers from the clinical notes. A major challenge for phenotyping and cohort identification is that administrative codes in structured electronic health records (HRs) do not completely capture who truly has epilepsy or which subtype they have. And NLP provide scalable way to overcome these limitations. So, for example, NLP can help detecting epilepsy presence from the clinical documentation, which may capture the cases that has been miscoded or absent from the structured EHRs. It can also help identify epilepsy subtypes by integrating textual descriptions with other structural information like medications, EEG findings, or SAD codes. Such a hybrid approach actually improves the granularity and the accuracy as well. And this kind of NLP capacity support large-scale, high-quality cohort building and enabling more reliable epidemiology studies and outcome research. These are some examples of NLP applications for phenotyping and cohort identification. Early in 2014, we developed a rule-based NLP system leveraging epilepsy and seizure ontology to extract epilepsy phenotypes such as seizure semiologies and EEG patterns and their associated anatomical locations from patient discharge summaries for cohort identification. Another work done by Finfurco Shajak in 2019 was another rule-based system for extracting epilepsy type, seizure frequency, medication, and other phenotypes from clinical letters. And in 2023, Shafajuri also developed a machine learning-based NLP methods to identify children with refractory status epilepticus. The machine learning model they used was the spot vector machine. In 2023, Barber developed a simple rule-based NLP system with a keyword search to identify rare epilepsy cohorts from clinical notes. Same year, Fernandez developed machine learning-based NLP methods, leveraging clinical notes, FZD codes, and anti-seizure medications to identify epilepsy patients. The machine learning method they used was the logistic regression and XGBoost. In the recent late 2025 file, used open source large language models, Llama and Mistral, to actually extract epilepsy-related information such as epilepsy type, serotype, current anti-seizure medications, and associated symptoms from the clinical letters. Altogether, these studies has shown the evolution of the NLP techniques from rule-based to machine learning-based and then to more recent large language model-based approaches. For NLP applications in seizure frequency and outcome extraction, Becker's work in 2022 demonstrated that rule-based NLP was able to identify seizure types and the seizure frequency phrases from clinical notes. And CS work in 2022 demonstrated that fine-tuning pre-trained bird-based models was able to extract seizure frequency and seizure freedom information from clinical notes. And then in 2024, Fernandez actually used the Xie's fine-tuned model to actually extract serial control metrics for data of last seizure and seizure frequency. So demonstrating that the pre-trained bird-based models by Xie can be generalized across different data sets. Machine learning-based NLP has been used for identify surgical candidates for epilepsy. All this work listed here are based on machine learning models such as support vector machines, logistic regression, XGBoost, and random forest, and so on. There have also been discussions and recommendations by Maura and other colleagues for integration of NLP and large language models into neurology clinical care, which brings both promise and challenges. So awareness of both these factors is very critical to realizing NLP and AI's potential for improving patient safety and care quality. NLP applications related more to SUDEP is risk marker extraction. In 2029, Bauer developed rule-based NLP to identify variables associated with 3 SUDEP risk factors, including generalized tonic-clonic seizures, refractory epilepsy, and surgical candidacy. And in 2023, Tao developed a rule-based NLP system to extract the first seizure onset time. And more recently, our work for developing fine-tuned pre-trained language models to extract seizure frequencies to facilitate SUDEP risk assessment. So next, I will focus on introducing our recent work for the seizure frequency extraction, published in NPJ Digital Medicine. As many of you know, high seizure frequency is a major SUDEP risk factor, and the seizure frequency information has often been described in free text in clinical notes or epilepsy evaluation reports, like showed in this light blue box. And automatically extracting, seizure frequency information from the free text, it will be very helpful for facilitating SUDEP risk assessment. In our work, we designed 2 different tasks. One is for extracting seizure frequency phrases, for example, the GTC 1 every 5 to 6 months, and the other is for extracting more detailed seizure frequency attributes, which actually contains more fine-grained attributes like event, quantities, maximum and minimum durations, and also the temporal unit. This is a more comprehensive list of attribute types we modeled in this work, with examples shown here. For the final extraction, we combine the results of phrase extraction and the attribute extraction together to obtain the more structured, detailed seizure frequency attributes, like as shown in these 2 tables. This is the overall workflow of our seizure frequency extraction framework. So the left branch is for seizure frequency phrase extraction, and the right branch is for the seizure frequency attribute extraction. For dataset, we prepared over 2,000 free text segments from epilepsy evaluation reports from 6 institutions, and randomly selected 800 instances for annotation and split them for training, validating, and testing. And we fine-tuned both bird-based models and large language models for the extraction tasks. And this is the evaluation performance. Use different models for phrase extraction and attribute extraction. The using GPT-4 for both serial frequency freeze extraction and the serial attribute extraction achieved the best performance. The results shows that fine-tuned large language models has a potential for extracting structural serial frequency details from the free text evaluation reports. And another indication of our work is that it provides a standard approach for representing or modeling the serial frequency attributes. This is similar to the SUDEP common data elements effort for data standardization. One limitation of this work is we didn't consider serial freedom as part of the NLP task here. So if we don't have any serial frequency information extracted, it does not indicate it's serial free. And for our ongoing work, we have been working on building a more comprehensive SUDEP risk factor vocabulary, and then expand our automated extraction framework to other SUDEP risk factors as well. In conclusion, this work shows that NLP offers a scalable way to convert free text serial frequency description into a more structured and machine-readable format, and then enabling the automated SUDEP risk quantification and assessment. And also, the serial frequencies extraction framework actually represents a very fundamental component for us to build a more comprehensive and systematic system for SUDEP risk marker extraction. Last but not the least, I would like to thank my collaborators, Drs. Zhang, Lhatoo, Tao, and Abhishek, and also the funding support from NINDS. Thank you for your attention.
Thank you, Dr. Kui. And to wrap it up, it's my pleasure to introduce Dr. Benjamin Brinkmann, who's professor of neurology at the Mayo Clinic. He's talking to us about his work in seizure forecasting. Ben?
Thank you, Jeff, for that kind introduction. I realize I'm standing between all of you and dinner, and I guess the award ceremony. So I'll try to be brief. And I unfortunately didn't put any slides of Jeff on a motorcycle in my talk today, but with a comment about the Holy Grail, maybe I should have put some Monty Python in, perhaps. But maybe next time. These are my disclosures. I do work a fair bit with industry, and I think that's sort of necessary in what I do. My talks tonight is going to be fairly general, so I won't be talking about much that's off-label. As alluded to before by earlier speakers, when we talk to people with epilepsy and we do surveys, and there are several published surveys that support this, they routinely say that it's the apparent unpredictability of seizures is something that drives a real sense of limitation with epilepsy. And you think about it, limitations on activities, they're all driven by the fact that a seizure could occur. Obviously, people have seizures a few times a month sometimes, but that colors what they can do, that prevents them from doing certain things. And sometimes that's a source of anxiety when people don't know when the seizures are coming. Of course, we treat epilepsy by giving people medicines every day. They have side effects every day. If we had better information about when the seizures were going to occur, maybe we could modulate those medications, give them fewer side effects on low-risk days. That's an interesting possibility that we're investigating. We'll talk about that in a moment here. And of course, there are neuromodulation therapies, the RNS, the VNS, the DBS devices. We set those levels, and they're pretty much static all the time. That seems to be the way they work best. But gosh, what if we knew when the seizure was coming? Maybe we could increase that a little bit the day before, and maybe prevent seizures before they happen. That's really the hope. Now, how does seizure forecasting happen? We used to call it seizure prediction. I don't know, maybe some people still do. I don't like that term just because, I don't know, it conjures up, to me it conjures up an image of a person with a crystal ball, or, seems to say that we're perfect at it. We're far from perfect at it. The way seizure forecasting works, and I like forecasting because it's a bit like the weather. The weatherman gets it wrong sometimes, but most of the time they're pretty much on. And that's about where we are with seizures too, I think. We're looking for patterns, just like your weather forecaster is looking for how rain showers are moving across the Midwest and projecting what's going to happen. That's exactly the same thing that we do with seizures. So this is an example of a patient who was recorded at King's College London with a subscalp EEG device. This is an electrode that goes under the skin and records seizures. If you look on the vertical axis there, it's time of day, so midnight's in the middle, noon it sort of wraps around, so it's at the top and the bottom of the graph. And every column in that graph is a day. This person was monitored for 230 days with the device, and ignore the blue color and that sort of thing. But you can see the little boxes and stars are when her seizures happened. And she's got a fairly consistent pattern. It's middle of the night, after midnight, most of her seizures are coming. It's not perfectly consistent, but that's a pattern. We look at these things. Well, there's the pattern. You guys probably saw it already. We can take these patterns and we can plot them out to try to make it a little more obvious, looking at the time of day in that first plot there. And this data is from a different person, so it may not line up with what I just showed you. But many people actually have very strong daily patterns with their seizures. Weekly cycles can be another one. Sometimes monthly cycles appear. And then there are cycles that don't seem to correspond to any sort of logical time period. There's a 13-day cycle in some people. We're not sure why they happen. There are some theories, but we can look at these cycles and we can say, all right, so when we look at your seizures, they typically happen in the afternoon, and it's every 11 days. So we can project that out and we can say, yeah, maybe you're at higher risk. You had a seizure today. 11 days from now, you might be at higher risk. So that's one way we do it. The second way we do it is looking at just applying AI algorithms to the data. This is from one of our papers. This is wearable data from the Empatica device, and we took all of this. We measured people's just measured their physiological activity with a wearable device for about a year. Really long-term data is immensely helpful for working on seizure forecasting. And we sent all of this data to an AI algorithm, and in this case, the seizure happened there. And we found that, so we've done this with wearables, we've done this with implanted EEG devices, and we found that we're able to forecast many of people's seizures. We do have some false alarms, and we're not perfect. So, I think the best results we've seen are we're forecasting, say, 85 to 90% of someone's seizures, and we're having several false alarms, maybe one or two false alarms a week, perhaps. Again, depending on the approach, and these are some devices that we've used for seizure forecasting. This is, I think, where the current modern era of seizure forecasting started, with these long-term invasive EEG devices. These were people who had electrodes implanted in their brains and were monitored for, again, very long periods of time. A group of a study that was done in Australia with the NeuroVista device. This was 2013, this was published, so a fair bit of time ago. And then our group has worked with a device from Medtronic that could also record. It's a deep brain stimulator, so it would stimulate, provide therapy, and record. And again, with these approaches, we mostly did the AI approach, but the Melbourne group has done quite a lot and pioneered looking at cycles, looking at the timing of seizures. The Epilepsy Foundation supported a collaboration with our group and King's College London and the University of Melbourne to do seizure forecasting using just wearable devices. We were fairly successful. This is sort of the culmination of that effort. We looked at a lot of different wearable devices. We did quite a bit of work with data processing and tested many different algorithms and used what we'd learned previously with the invasive EEG devices. Using just a wristwatch and, of course, a seizure diary, because we need to know when the seizures happen, we combined the cyclical models with the AI models, and we're able to, for many people with epilepsy that we studied, we were able to forecast their seizures better than a random predictor, and that sort of tends to be the standard we use. There's some debate about whether we need better standards for a baseline comparator, and at what point are our results clinically useful to someone, because I think forecasting is not perfect. It probably never will be, I think, because of the physiology, but also because of our measurement techniques and our analysis techniques, the AI algorithms. But we had 80% sensitivity just using the wristwatch, and this was 11 patients who were studied for 8 to 12 months. So yeah, predicted 80% of their seizures and had maybe a false positive every week, something like that. And so that's the best we've been able to do. Now, we're still working on this problem, and I think we're very pleased with the results so far, but I think we're still maybe a step away from being really clinically useful. And then the question becomes as well, okay, if we have this information, we're at a higher risk of seizure, what do we do with it? So this is our current study. We called it the Foresight Trial, Forecasting Seizures to Initiate Therapy, and also because every trial has to have a cool acronym, right? And this was generated by ChatGPT, or partially generated. Just a little illustration there. But the idea is, I think, fairly simple. We're taking the subcutaneous EEG device that I talked about earlier, and we've done some forecasting with those signals. It works pretty well. We're also taking an Apple Watch and recording heart rate and step counts with that. We have to monitor people for a certain amount of time to learn what their seizure patterns are. And then our algorithm and our system will send a push notification in the morning on the day if you're at high seizure risk. The eventual plan, and I have to put a caveat in here, the eventual plan is to have people take a rescue medicine, essentially, before the seizures start on their high-risk days. We have the FDA has approved an investigational device exemption for us to do the study without the medication. So we're going about this progressively, but we're going back to them now to ask for permission or approval to add the medication to the trial. The hope is that we could prevent seizures before they happen, and that maybe providing this acute preventative medication would be more effective than, say, adding another anti-seizure medicine with all the side effects that go with it, of course. And we're still working out the dosing of what's the proper dosing. Do we do a full rescue dose, which really makes people kind of sleepy? Maybe that's acceptable if you're not going to have a seizure otherwise, but we're still working that out a bit. Summary points, just want to let you know that we are working hard on this. We are making progress. Everything does take a long time, unfortunately. We were talking earlier about the regulatory piece and just how we, have conversations with the FDA and our local IRBs, and it's all important, but it just takes time. I want to make the point as well that seizure forecasting, it's not perfect. I think it never will be, but I think we can do better too, and we're working hard at that. Of course, this conference is focused on mortality. Can seizure forecasting do anything to help prevent mortality? I'm not sure. Maybe for a few very specific cases, if your seizure patterns are very regular, very clear, maybe then we could know when a person's at higher risk, maybe we could have a caregiver watching or something like that, kind of reduce that burden a bit on parents in the case with a child. But I think for most people with epilepsy, I don't think we're accurate enough, really. And then I think the important thing that I just want to stress as well is seizure forecasting isn't accurate enough for someone to drive a car or go swimming or do something that wouldn't be safe just based on the forecast, of course. And I think forecasting may be useful to guide therapy. One thing that we haven't explored that I think is sort of low-hanging fruit and we really need to delve into is this idea of, can we do a magnet swipe on somebody's VNS, before on one of their high-risk days, or do a few magnet swipes. I think that's a study that needs to be done. DBS, RNS as well. Those things might be available. I think the RNS angle is being pursued, and lots of studies are underway. So, and thank you very much. We are anyway. If you have questions, please reach out. And if you're curious about our study, the QR code there on the bottom will take you to the clinicaltrials.gov page.
Thanks, Ben. Really, thanks everyone. This is pretty exciting stuff, and it's happening now, and it's going to occur just in the next few years. So, in terms of how this is going to affect people's lives, I think it's going to happen, and relatively soon. At least I hope it is. So, we have time for a couple questions.
Hi, sorry, this is a question for Dr. Tellez. Apologies if I pronounce your surname wrong. So we know that sleep and epilepsy and seizures are incredibly important, and there's tons of data out there. At what point, as a clinician, do you suggest a patient to get a sleep study? Is it when they're starting to have complaints about sleep, or should it be done through the whole, first diagnostic process?
That's, sorry, that was hard. That's a really good question. But definitely a clinician should answer it. PhD, but not MD. But based on the data that we worked on, the thing, I think it's, because we've seen this very important, like through all these talks, I think at least maybe one should definitely be recommended. You should definitely talk to your epileptologist, physician, whatsoever, but definitely bring up the idea, because that would be really helpful to have at least one, so then we can see what your normal sleep would look like. And if you do it on a good sleep lab, which are already specialized for these, they already have the advanced algorithms, they can just do it way faster and better than we do at the AMU, then definitely that can bring us a clue of what is the patient's baseline sleep. So then we can see, is this normal, is this abnormal? Could this clue us on more forward on what to do? Oh, yeah.
Yeah, so I think for many of us, clinicians working in epilepsy, we keep a very low threshold for doing sleep studies. Definitely if patients complain of sleep problems, we do them, and in cases of intractability, we look, we search very hard to see if, sleep's a factor. One of the things that we don't do very well is take advantage of sleep recordings in the epilepsy monitoring unit, because in the monitoring unit, patients are sleeping there, and in fact, a lot of the research that Oman did in the Center for SUDEP Research Data is sleep data that comes from the EMU, and we really don't, use that information very well currently as part of our clinical workflow. So that's something to think about.
University for epilepsy risk factor investigation, and we found if you put more risk factor in it, your result will be changed. This paper just published in JAMA Neurology 3 weeks ago. So can you tell me how many variables you put into your testing model and how many rounds of testing you have made before you make the final model to get your results?
That's a very fantastic good question. The full scope of the project that we did, which this work was published as well in the journal, in the Lancet Neurology, we consider both breathing and respiratory and sleep features. From the sleep one, we included the slow wave activity, which is that line that we observe in our patients. We included a lot of more common micro architectures, such as time spent in sleep stages, wake after sleep onset. We included as well microarchitecture, so EEG-based features as well, powers in delta, alpha, all those bands. For the regards of the breathing, we had some of these patients also had the bands breathing during the night, so we're able to take 5 minutes of uninterrupted sleep during non-REM that we took as well breath intervals, specifically the mean, median, standard deviation, coefficient of variability. So we melded all of this together, and it was the help of Dr. Rossi, who was a biostatistician at UT, who helped us with this. And we were able to obtain that we're capable of separating between the SUDEP and high risk of SUDEP patients and the low risk of SUDEP and control patients when we look into the slope as well as the coefficient of variability of the breathing pattern. So the specific test for what he did, it was, I believe was 10,000 iterations for these features going back and forth to see which one were the strongest ones. But we're still searching for more clues and ideas of what to do. Because again, the slope that we calculated was only using the generalized tonic-clonic as a separating variable. But we're looking into more ideas of what else could we add for the patients. Genetic variables, we can include medication, all that type of stuff that we can then use to further broaden that search into more standard and robust biomarkers.
Can I go? Oh, hey.
Please, Elizabeth.
Hi. For Dr. Brinkmann, thank you very much. First of all, great panel and very interesting and exciting, obviously. Can you tell us a little bit more about what's considered successful forecasting as far as like the timeline? So it would be very different information for my patient to hear you have seizures on Sundays versus you're going to have a seizure in 6 hours, 1 hour, 3 minutes.
Good question, and it's an area that I don't think there's consensus among at least in the research community on. With our work, so with the cycles work, one of the things that I really like about that is it gives you a lot of time. So you can say, Sunday's a high-risk day. That seems to be fairly helpful for patients. With the AI work, a lot of our studies, it was about 20 minutes of warning before the seizure would happen. 20 to 30 minutes, I think, of warning is what we were typically getting. I guess that's just driven by the data and what we're able to do.
Thanks, everyone. Great panel.